All right. Well, you're probably familiar, at least in passing, with the SI system, the International System of Measurements that we've agreed upon as scientists. We're going to use these uh, particular units in other, to basically have a common language to discuss things. Now, perhaps something you didn't know about the SI system is that there are only 7, plus or minus a few, base units. The other ones can be used for measuring things, like angles and such, that don't have actual physical meanings, but the other ones do. They have physical definitions. The SI base units are the meter, which, well, it's a meter. Its length, it's a little longer than 3 feet. Second is also a base unit. It's, 1 1,000, 2 1,000, 3 1,000, that sort of thing. The kilogram, interestingly enough, it's the kilogram. It is not the gram. You have to have kg if you're looking for the base unit. The gram is a derived unit from the base unit of kilogram. Amp, which is a unit of electrical current, so basically how many electrons are flowing past a point at a given time, given by amps, or protons, or what have you. Kelvin is the SI base unit of temperature. Whether you're familiar with the Kelvin scale or not, it's basically a Kelvin is equivalent to a Celsius degree, only the Kelvin scale is set at 0, at absolute 0, the coldest temperature you can get to, which is a nice place to put your 0. And there's some others which are less commonly used in physics, but definitely commonly used in other places. Well, okay, these down here are your theoretical units. They're derived using mathematics rather than particular physical constants. A mole is an amount of substance. It's about equal to 6.02 times 10 to the 23rd of something. So that's just a number, a very, very large number, but still just a number. And a candela is a unit of how bright something is, intensity of light. We don't use candela too often, but we will use meter, second, kilogram, and ampere, and Kelvin quite a lot, and mole somewhat as well. Radians and steradians. Well, a radian is sort of like degrees, only it's defined more in terms of pi. In a circle, there are 2 pi radians. And that was probably one of the worst circles I've ever drawn. Or 360 degrees. You say there's 2 pi radians, you say there's 360 degrees, you're saying the same thing. So 1 radian, since 360 to 2 pi, if you know your ratios, it'll be 180 to 1 pi. 1 radian is equal to 180 degrees over pi. So there's your conversion. If you've got a radian, you can multiply. Now, getting back to the other base units up here, the meter, the second, the kilogram, the amp, so on and so forth, you might think, but wait, I've heard of things. I've heard of other units. I've heard of a Newton for force. I mean, this only covers what? You've got length, time, mass. Now I write mass, not weight, because there's a distinction between mass and weight. Ampere is current. But what about charge? That's not a base unit. If you want to get charge, you have to take your amperes and multiply by seconds, because an ampere is defined as charge per second. Kelvin is temperature. Well, there's all kinds of things. There's force, there's power, there's electric field, so on and so forth. But I assert that we can define all of these in terms of our base units. Let's take a rather easy example as force. Force, I'm going to put brackets, these square brackets around something to say, give me the units of this. You say, Mr. Roden, I know, force is a Newton. Force is a Newton. Yes, that's true. But if you remember Newton's laws, force is equal to your mass times your acceleration. And if you remember that acceleration's units are defined in terms of these base units as how many meters per second something changes in a given second, which is meters per second squared. So that means if I want the units of force, a Newton is the same as saying, well, the base unit of mass is a kilogram. The base unit of acceleration is meters per second squared. And now look at that. A Newton has been defined in terms of these base units. And you can get even more complicated based on, all you have to do is go back to whatever formula you're working with. For instance, work, as long as you're moving perpendicular to your motion, work is defined as force times distance. If it's off at an angle, there's a correction factor based on how much of an angle it is. But essentially, you can get the units for work by looking at the base units of force and the base units of distance. Now, we know, or we will learn, that the base unit of work is a joule, same as energy, which means a joule can be broken down into force, which is, we said, a kilogram meters per second squared, because that's what a Newton is, times the unit of distance, that's length, that's a meter. So I can actually combine this m and this m, call that m squared. So the base unit of work, or a joule, is equivalent to kilogram meters squared per second squared. And if you happen to remember formulas for other things, and you happen to know those base units from those formulas, you can get all kinds of crazy things. Just off the top of my head, I want to know, say, what's the base unit of electric or magnetic field? Magnetic field I usually see represented with B. I remember the force on a current carrying wire is BIL times sine of theta, L being the length of the wire, I being the current flowing through the wire, F being the force on that wire. The sine of theta is unitless, so I'm going to neglect it. We're going to assume this is perpendicular. And then basically I want to solve this for B, so I'm going to divide both sides by IL, canceling out the things on this side, put IL over here. So this magnetic field is now basically, it's your force over current times length, okay? So if we want the units of these, we look at the units of all these particular bits. Now we said current is amp. That's the SI base unit, so we go ahead and write that. We said length is meter. That's our SI base unit. That's the bottom already taken care of. And again, our force is our kilogram meters per second squared. Now this per second squared is kind of annoying right there, so I'm going to go ahead and write this kilogram meter over amp meter times just the 1 over second squared. I can do that. I can move him over because it's all multiplication. And would you look at that, there's a meter in both the top and the bottom. Those meters cancel out, and we are left with kilogram, the meters are gone, per amp second squared, which is a really hard thing to wrap your mind around what it actually means. I mean, it's how many kilograms there are per amp second squared? I'm not sure. But that's the SI base unit of magnetic field. There's kind of a reason we tend to define it as Tesla. We would only write T for this. In the same sense, we would write N for force, watt for power, which we can break down, so on and so forth. But these are just shorthand, the base units. Everything can be broken down into these base units, which to me is quite interesting.